Okay, today we are going to start with the next three physical quantities, work, energy, and power. Okay, so we are going to go through the definition of each of these physical quantities and also get to learn the units, okay, the equations, and how are they related in our study of kinematics. Okay, so in the picture that you see in front of you, you have there a Greek god. His name is Atlas. He's supposed to be carrying the globe over his shoulder, and that globe is the Earth. And the question that will be posed later is whether Atlas is producing work while he is carrying the globe. Okay, let's go through the physicist's definition of work. So we define work in physics as the force multiplied by the displacement of an object. Okay, force is a vector quantity, displacement is a vector quantity, but work is a scalar quantity. Okay, this will be explained later. Now, force and displacement, they should be acting on the same line of action. Okay, so they could be heading towards the same direction, or force and displacement could be in the opposite direction, meaning you are exerting force to the right, but the displacement is to the left. Now, is that possible? For gravity, it is possible. Okay. Uh, Now, if you have force and displacement moving in the same direction, you will get positive work. But if force and displacement are in opposite direction, you will get negative work. Okay. Now remember that work is a scalar quantity. Okay. So you have here the formula. Work is force multiplied by displacement. Okay. Again, work is a scalar quantity. It is not a vector. Okay, so as you can see, Atlas holds up the Earth, but he doesn't move. So the displacement is equal to zero. Okay, the displacement is equal to zero. Since the displacement is equal to zero, Atlas does not do any work. Okay, so you see the equation work is equal to zero. He doesn't do any work. Okay, let's take a look at this person. Garcon does work when he picks up the tray. So he picks up the tray. The weight of the object is downward, the force is upward, okay, and there is displacement, okay. Now the displacement is not zero, so when while picking up the tray, there is work, but when Garcon is carrying the tray around the room, the displacement, okay, is zero. Okay, therefore, while he's carrying it around the room, okay, there is no displacement. Okay, now why do we have this definition? We got this from Newton's second law of motion. Okay, so Newton's second law says that force is equal to mass times acceleration. Now, this is explained best by calculus. Now, you have the definition of work, which is force multiplied by the displacement. You have a little of calculus. Okay, you would be able to derive work is equal to change in the kinetic energy. The equation 1 half mv squared refers to the kinetic energy of an object, of a moving object in particular. Okay, so we expect that work and energy will have the same set of units. Okay, so what would be the unit of work? Okay, let's go back to the equation. W is F times D. In the MKS system, if force is in Newton, sorry, it's in Newton, and displacement is in meter, this would be Newton meter. And we have a special name for Newton meter that would be joules, and we capitalize the letter J, okay, when we abbreviate it. Okay, so this is an SI unit, yung joules. Okay, it's a derived unit. Okay, so F is a vector equation, but work is a scalar equation. Okay, now this scalar quantity is given a special name. As I mentioned a while ago, it is kinetic energy. Okay, let us have some sample problem. So, for example, a person is pushing this crate with a force equal to 30 newtons. And the displacement, after some time, there is a displacement of 4.0 meters. Okay, so what is the work done on this box? Okay, so work is equal to force, 30 newtons, multiplied by 4.0 meters. Okay, so 30 newtons times 3.0 meters, this will give us 120 Newton meter, or we can say 120 joules. Okay, that would be our example. Now, if you exert this same force but not parallel, okay, but in this direction, okay, and the displacement is still 4.0 meters. Okay, so after some time, the box is displaced here, 4.0 meters. But the force that you exert, still 30 newtons, but it is at an angle of 30 degrees. Okay, so what matters here would be the F sub x, not the F sub y. So we have to get the x component of 30 newtons. Okay, so that would be work is equal to 30 cosine 30 multiplied by the displacement of 4.0 meters. Okay, so computing for that, what do we get? 30 times cos 30 times 4. This will give us 30 times cos times 4. Okay, this will give us 103.92 Newton meter, or we can have 100 joules. Okay, so pagka ginawa nating insignificant figures. All right, so let's have then another problem. Okay, so for example, you have to lift up an object, okay, upward. Okay, you exert a force of 50 newtons. Okay, and the displacement upward. Okay, so initially the box is at the ground. Okay, so the displacement upward is 4.0 newtons. Okay, so this 50 newtons would be upward force, no? So work is equal to F multiplied by, sorry, this one should be meters, multiplied by the displacement. So you exerted a force of 50 newtons, multiply this by 4.0 meters. Okay, this will give us 200 Newton meter, or 200 joules. Okay, now what if you have many forces acting? You have to get the net force. It's going to be the net force that will produce the work. So we did not consider the weight in this problem. But what if you are given the weight? Okay, let's say that the weight of the object is initially 40 newtons. Okay, that is FW. So FW is negative 40 newtons, and then you exerted a force upward, F equals to 50 newtons. Okay, what would happen here? Okay, what would happen here is you have to get the F net. The F net would be 50 minus 40, going to be 10 newtons. So the work is equal to 10 newtons multiplied by 4.0 meters. And this will give us 40 joules. Okay. Now, if you are asked, what is the work, okay, done by this one? Okay, the work done by FW, let us compute. The work done by FW would be FW multiplied by 4.0 meters. Now remember, that's negative, so negative 40 newtons multiplied by 4.0 meters. This will give us negative 160 Newton meter, or negative 160 joules. Okay. Now, what is the work done by this 50 Newton force? So, work is equal to F times 4.0. It will give us the same answer as this one, right? So, the force is 50 newtons times 4.0 meters. This will give us 200 joules. Now, what do you notice about what we did here? Okay, so when you subtract 200 joules minus 160 joules, you will get 40 joules. Okay, so this is the work, okay, that is in effect. Okay, but each of the components, like yung 50 newtons and the negative 40 newtons, we have also work done. So the total work, okay, in effect is 40 joules. Now this work here, the 160 joules, is what we call the work done by gravity. All right, this is the work done by gravity. So if the question is just asking for the work done by gravity, then this would be the solution. And if it's asking for the work done by the 50 Newton force, then the answer would be 200 joules. Okay, and what is the um, total work? It's going to be just 40 joules, the net work that was done. Okay, okay, let's have another problem where you have forces that are not parallel, or forces that are not on the same line of action, no, as the displacement. So, for example, you have F here to be 60.0 newtons, and this is at an angle of 60 degrees. Now, the displacement, the given displacement is 5.0 meters. What is the work done? Okay, so work is equal to the x component, because the x component is the one that is in the same line of action as the displacement. So f sub x times 5.0 meters. But what is f sub x? F sub x is 60.0 newtons, cosine 60 multiplied by 5.0 meters. So 60 times cos 60 is zero point 0.5 times 50, 5.0 meters. Okay, so this is 30 newtons multiplied by 5.0 meters. This will give us 150 joules. Okay, now we say that work is can be equal to the change in kinetic energy if the object is moving. Now, if the object is not moving, but you have stored energy, then work is equal to the change in potential energy. So we take a look at the two instances wherein work is equal to the two types of energy mentioned. Okay, so this equation that you see in front of you, yung work is equal to change in kinetic energy, is what we call the work energy equation. So this is the first one. So later on, we are going to equate work with potential energy. Okay, so let's look at the units again. So kinetic energy is 1/2 mv squared. M is the mass, v is the speed of an object. Okay, mass is in kilograms. When you square velocity, you get meter squared, second squared. Okay, and we know that work is force multiplied by displacement. So Newton, meter, you get kilogram meter per second squared multiplied by meter. So they are the same, right? So you see that these two are will have the same set of units. So this one, kilogram meter per second squared, is from Newton. Remember, second law. And then this one, meter, is from displacement. Okay? So they are numerically equivalent to the unit we call joule. If you're going to write joule in its entirety, you can use small letter. But if you're going to abbreviate it, then you have to capitalize the letter J. Now, joule is an SI unit, so you can attach any prefix you want. So pwede siyang maging kilojoules, okay, gigajoules, megajoules, okay, etc. Any of the metric unit prefixes can be attached to it. Okay, so let's go to the work energy theorem. Where is this used? Kinetic energy. When you say kinetic energy change, okay, delta symbol, it means KE final minus KE initial. Okay, so KE final, when you expand this, you have mv square, final squared minus 1 half mv initial squared. Now, the mass and the mass final and initial, they are the same, so you can factor them out, 1 half m. And then this becomes v sub f squared minus v sub I squared. Okay, let us apply this unit. Okay, so let's say you have a gun and there is a bullet here. Okay, and then when you click on the trigger, of course, the gun explodes and the bullet travels from this point to this point. Okay, let's say that, so initially here, the kinetic energy is equal to 0 because the bullet is at rest. Okay, so once the bullet reaches this, the muzzle, okay, we call this the muzzle, this portion of the gun, okay, the velocity is already at 200 meters per second. Now, assuming that the bullet has a mass of 0.15 kilograms or 150 grams, okay, and you are asked what is the kinetic energy change. Okay, so the delta KE is equal to K final minus K initial. K initial is 0, so delta KE is just KF, right? And we can solve that. Okay, 1 half the mass of the object, 0.15, and then the speed of the bullet, 200 meters per second, and then you square it. So the change in kinetic energy is equal to 200 squared times 0.15 divided by 2. So the change in kinetic energy is 3,000 joules. And the work exerted by the gun, okay, nag-explode kasi siya, no, would be also 3,000 joules. Okay, this is the work energy theorem. Okay, let's have another example on this. Okay, let's say that initially a cart is moving at a speed of 5.0 meters per second. Okay, let that be V initial. And then there is a force exerted on this cart, okay, that led it to move and change its speed to 10.0 meters per second. And the mass of the cart is equal to, let's say, 20 kilograms. And then you are asked how much work was done on the cart. So we use the work energy theorem equation that we derived a while ago. You have 1 half m, okay, v final squared minus v initial squared. Okay, so the mass is given. The mass of the cart is 20 kilograms multiplied by the v final is 10.0 squared minus the v initial, which is 5.0 squared. Okay, solving for this, you get 1 half 20 kilograms. This will give us 100. The unit would be meter squared, second squared, minus 25 meter squared per second squared. Okay, this will be 1 half times 20 kilograms multiplied by, what is 100 minus 25? This is 75 meters squared per second squared. Now we know that when you multiply these units, you put them together, kilogram meters squared per second squared is actually the joules. Okay, so the work done because of the push of this object would be, let's compute, 750, okay, 750 joules. Okay, so that is the work done on the object. This is also the change in kinetic energy. Okay, now at the start of this lesson, we have mentioned yung work done by gravity. Now, the work done by gravity is always pointed downward because gravity is the pull of the Earth, okay, on an object. Okay, it's the force of attraction between the object and the Earth. Okay, so let's say you have this. Okay, this object started in this side, then it ended on that side. So the displacement that we have to get is in this one, yung straight line distance. No, by definition, displacement is the straight line distance from where you started up to where you ended. Okay, so the displacement, okay, that we have to get is this one. Okay, and change in vertical height meron din. So straight line lang. Okay, so force multiplied by the displacement. Now the force is negative mg multiplied by the change in height. Okay, so what do we get here? That would be the work done by gravity. Okay, so gravitational potential energy is work. Okay, gravity is equal to the negative change in um, the potential energy. mgh is potential energy. This is mass multiplied by the gravity, 9.8 meters per second squared, multiplied by the height. Okay, so this is called gravitational potential energy or PE grav. Okay, or sometimes some of the textbooks would write capital GPE. Okay, to refer to gravitational potential energy. Okay. Now, the work done by gravity is equal to the negative change in PE. Okay, negative change in PE. Okay, remember this. And the change in PE is equal to, just inano lang niya, no? Change lang niya yung position. Okay, change in PE grav is equal to negative work gravity. If gravity is the only force doing work, okay, your work energy theorem will be reduced to this one. So negative change in potential energy is equal to change in 1 half mv squared. This becomes 0, right? So you have 0 is equal to change in mgh, magiging 0 ito. Okay? So mgh plus 1 half mv squared is equal to a constant. Okay? This is the complete version of the work energy theorem. So taken into account yung change in potential energy and also the movement of the object if the object is moving. Okay, let's have a sample problem on this. So work is equal to the negative change in potential energy. What is potential energy? Sabi natin mg H final minus MGH initial. Okay? So, kapag dinistribute natin, you get MGH initial plus MGH final. Okay? So, negative times positive, you will get, uh, wait, MGF will be minus na to. Sorry. Nagbaliktad sila. And MGHI will become positive. Okay? So pagka dinistribute mo. So this work is equal to negative delta PE, the negative change in potential energy. Okay, so let's say that initially you have a mass here, 5.0 kilograms, and then you placed it higher. Okay. Siyempre, the mass would still be the same, 5.0 kilograms. You place it higher, nag-display siya ng 4.0 meters. What is the work done when you did this? Okay, so work is equal to, of course, this one we can factor out m times g. You are going to get hi minus hf. Okay, so the initial height is equal to 0, and then the final height is 5 kilograms. So the mass of the object multiplied by, and then 0 minus 4.0 meters. Okay, so what is the work that you are going to get? You are going to get negative 5 times 9.8 times 4. You will get negative 196 newtons. Newton meter, or approximately negative 200 joules. Okay, so this is the work done. Okay, negative 196 by the gravity, no, by gravity. So for gravity, this will always be negative delta PE. All right. Now, what if we have a different situation? So, di ba, ito ang ating formula, no? Negative delta PE. And we say that delta, the change is PE final minus PE initial. Now, initially, paano kung ang unang position is here, tapos binaba mo? What happens? Okay, so dito muna siya. 5.0 kilograms, tapos binaba mo ng 4.0 meters. What is now the change in potential energy? So W is equal to negative delta PE. Okay, so we expand this. PE is mg h final minus mg h initial. All right. Sorry, there should be an equal sign here. Okay, so pagka distribute, you are going to get mg, okay? So hi minus hf, okay? So mg, okay, h initial, it's the h initial is 4.0, tapos h final nilagay mo sa lapag kaya naging 0, okay? So you are going to get mass niya, no, 5.0 times 9.8 times 4.0. This is going to give us the same answer, but you are going to get positive this time. So 196 Newton meter or 200 joules this time around. Kasi you started, okay, from the top, tapos minove mo siya pababa. Okay? So you are not going against gravity. In fact, yung gravity kasi is downward di ba? So, same direction kayo, no? Downward. That's why it's positive 200 joules. Remember the one I mentioned at the start, if the force and the displacement are in the same direction, you will get positive work. If the force and the displacement are in opposite directions, you will get negative work, just like this one here. Kasi yung force of gravity kasi is downward, right? And then you are displacing it upward, 4.0 meters. That's why you got a negative answer here, okay? So that's it for today, and we are going to have more problems on this next time. Thank you very much.